Good morning, everyone. Today, we are going to introduce the application of matrix in 3D engines. First, I want to introduce what a 3D engine is. A 3D engine is a software framework used to create 3D models or entire virtual environments. It provides developers with powerful tools so they don't have to write complex code from scratch every time they want to build a digital world. While we often associate them with video games, they are now essential in fields like professional design and industrial simulation. A modern 3D engine has these core functions. Rendering. This is the process of generating the final image you see on your screen. Physics. The engine calculates how objects fall, collide, or bounce based on real-world laws. Asset management. It organizes all the 3D models, textures, and sounds within a project. Animation displays characters and objects to life through movement. Scripting and programming. This allows developers to define the logics and rules of a virtual world. And these are the common 3D engines. Unreal Engine and Unity are the best non-gaming engines, from web games to AAA games. They can be seen everywhere. This two. This is Unreal Engine and this is Unity. And this one is Godot Gaming Engine. Godot is an open source 2D, 3D game engine. It has a small file size and easy to use scripts. You can even make a game with Godot on your Android phone. And this 3JSON is a JavaScript library that users can use to create and display 3D images in web browsers. It's usually used in interactive web pages, data visualization, building models, and even VR applications.
Hello everyone, in our engineering mathematics report, I'm responsible for exploring the fundamental mathematical pillar of 3D engine transformation matrices. Whether you are exploring a flat-made Wacom or using CAD software, every movement on screen is powered by 4x4 matrix multiplication to treat translation as a linear operation within a unified framework. We utilize homogeneous coordinate, extending our 3D vector into H, Y, Z, when format. First, let's look at the scaling matrix. Its function is intuitive. It modifies the size of an object along the H, Y, and Z axis. Mathematically, it is the most elegant structure. The scaling vector as H, as Y, as Z are placed directly on the main diagonal. If you want to double an object's width, you set SH to 2. This diagonal arrangement directly controls the expansion or contraction of a dimension. Next is the relation matrix. This is the most complex of the three because it involves trigonometry. It rolls to rotate an object around a specific axis. While we often use Euler angle for logics, they can lead to the infamous jumbo log. Therefore, in advanced engineering, we use quadrilinear for stability, but they are automatically converted back into these matrices for the GPU to process. Each combination of sine and cos essentially reproduces coordinate along a circular path. Finally, we have the translation matrix. In a traditional 3x3 matrix wall, we cannot achieve movement through multiplication alone. This is why the 4x4 matrix is vital. In this matrix, the translation value th, ty, tz are tracked into the last column. When multiplying by a vertex coordinates, it doesn't distort the shape. It simply acts as a navigation command, moving the object from one point in space to another. In 3D engines like Unity or Unreal, these three matrices aren't used in isolation. We multiply them together, usually in the order of W equal to T, R, S. Scale, then rotate, then translate. By combining them into a single matrix, the GPU can perform all three complex transformations in one single calculation, which is the secret behind the efficiency of modern rendering. Matrices are more than just grid of numbers. They are the tool we use to command the visual world. Thank you.
Hello everyone. Now let's dive into the core part of this report. How matrices handle spatial transformation in 3D engine. First, to show a 3D model on our screen, the engine goes through a pipeline of coordinate change. This involves three key matrix stages. On this page, the first one is model matrix. When an artist creates a 3D model, its points are defined relative to its own center. We call this local space. But in the game world, every object needs a specific spot. The model matrix moves the object from local space to world space. You can see the formula W equal to TRS. This stands for translate, rotate, and scale. Using these three steps, we can place an object or a character exactly where we want it in the game scene. Once the objects are placed, we need an observer, a camera. This brings us to the view matrix. The view matrix converts coordinates from world space to view coordinate. Here is a key concept. Moving a camera mathematically is actually quite complex, so we usually do the reverse. The view matrix is essentially the inverse of the camera's transformation in the world. Simply put, if we want the camera to move backward, mathematically we push the entire world forward. Through this matrix, we align the whole world to center around the camera. Now, let the world is aligned with the camera. But now we have a new problem. Our screen is flat, but the world is 3D. How do we photograph this 3D world onto a 2D screen? This is the job of the projection matrix. It decides how the 3D world is mapped onto your 2D display. There are two main types of projection. Let's look at it. On this image, the first type is orthographic projection. Look at this diagram. This is what you see engineering drawing or CAD software, the top view, front view, and side view. Its main feature is that objects look the same size no matter how far away they are. There is no depth perception. Things doesn't get smaller as they get farther. This page shows a matrix for this. This matrix basically does a linear mapping. It takes a defined box of space and flattens it directly onto the screen. This is great for strategy games or drawing UI menus. Let's go to the next page. This is perspective projection, which mimic how our human eyes work. Compare the two T-pop image. The right one using perspective clearly shows that objects closer to you look bigger. And this is the metric formula for perspective. You can see the variable z in there. This means depth is involved in the calculation. The coordinate x, y, z, and 1 transform into x prime, y prime, z prime, and w prime. The matrix map tree happens at the every end, called perspective dimension. We divide everything by w. This step makes distant objects appear closer to the center of the screen, creating the sense of distance. On this page, you can clearly see the flattened trapezoid shape. We have a near plane N and a far plane F. Only object into the shape will be seen. Everything too close or too far gets cut off or clipped. Finally, the shape is mapping into a range of from -1 to 1. This image shows what it looks like after the transformation. After the projection calculation, we don't just get the flat image, we got a wrap space. Look at the T-pop. After the projection transformation, that trapezoid view model becomes a perfect cube. This leads to the concept of NDC, normalized device coordinate. Whether your screen is Full HD or 4K, deep inside the GPU, all coordinates are standardized into a small box range from -1 to 1. The complex terms on this page are just mapped to stretch and fit the original camera view perfectly into the standardized box. Once in NDC, the GPU can efficiently decide which pixels to draw and which ones are hidden behind the object. In the end, we just discussed three metrics: model, view, and projection. In real game engine like Unity or Unreal, for performance we don't multiply these three times for every single point. Instead, we combine them into one MVP matrix beforehand. The formula is MVP equal to PBN. This way, for the thousands of metrics on the model, the GPU only needs to do one matrix multiplication per vertex. This huge efficiency boost allows us to play high-quality games smoothly at 60 frames per second.
Last but not least, let's move on to our conclusion. So, why we actually need matrices? To sum up, matrices are basically the engine of any 3D game. Without them, you can't even move a character on the screen. The MVP secret. The most important thing we learned is the MVP model view projection process. Instead of calculating every single movement separately, we can just multiply all the matrices together into one. This makes the math way faster for the computer, GPU, and efficiency. In games, everything happens in real time. Because matrices work so well with parallel processing, the GPU graphics card can handle millions of points at once. Basically, modern gaming only exists because we found a way to make matrix math super efficient. And here's our reflection. Before creating this report, most of our group members thought linear algebra was just some boring numerical calculations and formulas for passing exams. But after delving into the workings of 3D engines, we discovered that the matrices in textbooks are actually the physical laws that make the virtual world move. Seeing how a simple matrix multiplication can determine the distance and perspective a player sees in the game is truly amazing. This project has shifted our perspective significantly. We now understand that math is not just a theoretical requirement, but a powerful tool for building immersive digital experiences. Moving forward, we hope to apply this logic to our future studies in programming and software development, recognizing that a strong mathematical foundation is what makes high-level technology possible. This is our report. Thank all of you for joining today's presentation.